Welcome everybody to today's webinar by the IEA SHC Solar Academy and hosted by ICES. Please hold the line while we wait for all attendees to join, and we will begin shortly. Welcome everybody to today's webinar by the IEA SHC Solar Academy and hosted by ICES. Please hold the line and we will begin shortly. All right, welcome everybody to today's webinar by the IEA SHC Solar Academy and hosted by the International Solar Energy Society, ICES. We are very pleased to have all of you here. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ICES HQ in Freiburg, Germany, and I will give you a short introduction into ICES and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society, ICES, is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ICES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. And ICES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ICES, and you can always find more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings. ICES members can also get discounts and even free registration to ICES events and partner events. Every month, ICES publishes a newsletter for our members where you can follow our progress and share your news. And members can also subscribe to our academic journal Solar Energy, our flagship publication, at a reduced price. So we welcome those who are not yet a member to join us today to support our work. For those who are already a member, we thank you for your support. And as a special benefit to all attendees of today's webinar, we are very happy to offer a special discount when signing up as an ICES member. All attendees of this webinar will receive a 20% discount code as a follow-up over the coming days. Now, before we get into the webinar itself, a quick note on the Q&A session. We're going to have a Q&A session at the very end of the webinar after we have heard all of the presentations. And you can use your chat box to send in your questions at any time throughout the webinar. When you send in your question, keep them short, keep them precise, and ideally indicate who they are for so that our moderator can then easily assign them to any of the speakers. And now, with that, it's my pleasure to introduce you to our moderator for today, Bärbel Epp. Bärbel is the founder and managing director of the German consultancy Solrico, Solar Market Research and International Communication. She is responsible for the international newsletter on the portal Solar Thermal World and reporting exclusively about market and technology trends in the solar heating and cooling sector. And since many years, Bärbel has been the co-author of the SHC chapter of the annual Global Status Report by REN21. Now, I'm happy to hand over to Bärbel. Bärbel, thank you for joining us, and the floor is yours.
Thank you very much, Arabella. Good day, good morning, good afternoon, wherever you are in the world. I'm happy to welcome you to this new webinar today in the series of Solar Academy webinars of IEA SHC. And I will shortly introduce you what is the IEA Solar Heating and Cooling Technology Collaboration Program, a long name. It's a project-focused international R&D collaboration, quite old, 1977 founded. It has 19 member countries, the EC, and 8 international organizations. So you see that we cover all the colored countries on this map are members, and there are around 300 experts all around the world, partly from research, partly from industry, that group and work on solar thermal specific topics. And the topics they work on, we have listed here for you. They are currently 7 tasks, how we call these projects internally running. They are on industrial solar heat, efficient solar district heating, compact thermal energy storages, solar energy buildings, solar cooling for Sunbelt region, and solar neighborhoods. This is the one we have today. What can the Solar Academy offer you? Well, with these webinars, which we hold regularly by ISIS, mostly quarterly. Our next webinar is planned for March 22nd, 24th on global certification. And you find always the announcements either on the ISIS website or on the IEA SHC Solar Academy website. Also, you can look into a lot of videos that we have done with experts on past Academy webinars or conferences. And the Solar Academy offers on-site trainings. They are organized and held by the IEA SHC experts upon request of the member countries. And the past trainings have been as far-reaching as Caribbean, China, South Africa, and UK. Where to find more information? Certainly on the website. On the website, also each of these project areas have its own sub-web page. We have social media activities where you are happy to join. We have this YouTube channel I mentioned already, and if you have additional questions, you can contact the Secretariat of the IEA SHC program. So today we have an interesting group of researchers working on solar neighborhood planning. This task is called 63, so they are numbered by starting point. It's a 4 years project, so the researcher of this group are now halfway through their project, so they show us intermediate research results. And yeah, I think we will start straight away to introducing you the first of our speakers. So Maria Wall, she will hold the first speech, and she is Associated Professor at the Division of Energy and Building Design in Lund University in Sweden. She is Project Manager of Task 63 on solar neighborhood planning. And she has long-term experience in, organizing these big research groups, networks, as she was also chairing the previous task on solar energy in urban planning. So Maria Wall will give us a short introduction in what this whole task 63 is working about. So Maria, I'm looking forward to your speech.
Thank you, Bärbel. Let's see. So I hope you can see my screen.
Yes, perfect.
So I will give a brief overview of the project Solar Neighborhood Planning, and that you will hear more about today. And first I would like to kind of highlight what we can use solar energy for, all the benefits, all the good things with solar energy. I mean, we can use it for passive solar energy, both indoors and outdoors, to reduce heating demand and improve thermal comfort and health. We can also use it for daylighting buildings and outdoor areas to reduce electricity for lighting and to improve visual comfort and health. And we can use it for local renewable energy production using PV and solar thermal systems. And in this way, we can create energy or resource self-sufficient environments. So we don't need to rely on energy imports. And in this way, we can create resilience to energy price fluctuations. And we can use it for local food production and green areas to improve air quality and reducing stormwater. So we can really use it for a lot of things. But I think that we need to use it more efficient and more wisely in the future. I think we can improve this a lot. So the opportunities, examples of that for solar neighborhoods is that it is a means to achieve net zero energy districts and low carbon cities. And if we address both solar energy production and passive strategies when we plan neighborhoods, this enables us to identify synergies and to avoid conflicts between competing uses. So we shouldn't waste the possibilities to use available surfaces in neighborhoods. And we need to create long-term solar access. But this is very important. So if, for instance, if you have a building, if you have a house where you put solar panels on the roof, you don't want your neighbor to erect a building on the other side of the street just 1 year after, and destroying your solar gains and your investment. So you need really to have this secure access to solar access for a long time. And this is something we need to be better on when planning cities. Going to the project specifically, we started in 2019, and the project ends in 2023, the end of the year. And so we are midways now, and the objective is to support key players to achieve solar neighborhoods that really facilitate this long-term solar access with a good planning. And we work with and on new neighborhood development and to improve existing neighborhoods as well. And we deal with both active solar strategies and passive solar strategies. And we define a neighborhood as a group of buildings within a specific geographic area, often including different types of buildings and functions, open space and infrastructure. And the neighborhood can be part of a large city or an isolated community or something in between. So, and of course it can be connected to a district heating or cooling network or outside such. And this gives different boundary conditions that we have to take into account when planning. We organize ourselves in different subtasks and with different leaderships. And we have 4 subtasks. A, on solar planning strategies and concepts with a Canadian leadership. B, on economic strategies and stakeholder engagement with the Italian leadership. Subtask C, on solar planning tools with a joint leadership between Sweden and France. And subtask D, on case studies, which is jointly led by all the leaders, and we also have a coordinator helping us from Norway. And the case studies are really strongly connected to the other subtasks and topics where we work together with and collaborate with municipalities and the key stakeholders. And I am the general project leader. And the names here in red are the ones that you will meet today in the webinar. And the participating countries in our project are mainly some European countries, but also Australia, Canada, and China. So in total, we are 9 countries working on this. And with this, I stop my very brief introduction. Thank you for listening.
Thank you, Maria. Well, I think you really showed us how complex this issue is, solar neighborhood planning, and how surfaces are an important but limited resource in cities that aim to become climate neutral. I think this was a good introduction and an overview. So our next speaker, Caroline, I think Maria already introduced her as subtask A leader. She is from Canada, and because of the time zone, she cannot join us personally, but we will record her speech. She is an associated professor at the University of Calgary in Canada. Her research is focused on the impact of building shapes for solar potential and the development of multinational facades, among other subjects. Her research is very multidisciplinary. It brings together building engineering, architectural, and urban design. And she is, as Maria mentioned, the chair of this subgroup, which is called Subgroup A, and it's titled Developing Strategies for Net Zero Energy Solar Communities. So we will listen to her speech. Arabella, it's your turn.
Good morning. My name is Caroline Hashim Bermet. I am Associate Professor at the School of Architecture, Planning and Landscape at the University of Calgary in Canada. I'm also a leader of Subtask A, Solar Planning Strategies and Concepts within the IEA Task 63, Planning Solar Neighborhoods. I'll be talking today about some strategies and concepts for planning solar neighborhoods as part of the efforts and work that's done within Subtask A. Starting with a little bit of context, solar neighborhood planning is becoming significantly important as part of the efforts to reduce the environmental impact of increased urbanization, where by 2050 we are expecting that 70% or more of the world population to be residing in urban areas. Solar neighborhood relies on a holistic and integrated design approach that spans from the building components and building level to the urban level. Within this holistic approach, buildings and surrounding areas, including public spaces, landscape, streets, and street furniture, should be considered as active elements of the energy network rather than standalone energy consuming components of the grid. So at the building level, solar building design relies on passive designs in buildings. In fact, passive design is often attached to solar building designs. Improving solar access together with various design principles such as thermal mass, high insulation, airtight envelope are some of the basic principles of passive solar buildings. These principles can be implemented in all types of buildings, including residential buildings, including offices, institutional buildings, and others. Daylighting, passive heating of perimeter zones, passive and hybrid ventilation, coupling ventilation with solar chimneys, as we can see in some of these sketches, can significantly affect energy demand, reducing the energy consumption of buildings and their dependence on the local grid, which also can increase the resilience of buildings for climate shocks, and climate risks. Solar building design allows to improve energy efficiency of buildings, designing building shape, layout, and building envelope to maximize solar access and utilization within the building, affect the energy consumption of these buildings. It also allows better designed solar energy generation since well-designed building envelope can be exploited to integrate solar technologies such as photovoltaic systems, such as thermal collectors or hybrid photovoltaic thermal systems for the generation of electric and thermal energy. Talking a little bit about building envelope design and the integration of technology. In fact, building envelope can be optimized to maximize the surface area and the exposure to solar radiation while presenting architectural and aesthetic flexibility. These are some examples of a theoretical study that was done by myself and my group at the Solar Lab at the University of Calgary, where we try to optimize the building envelope shape geometry through a different design of folded plates that allows maximizing solar radiation on these plates. This also, we were integrating different type of photovoltaic system in different colors. At the level of neighborhood, many aspects affect an optimal solar planning. For example, the type of neighborhoods the building mix presents can affect the building designs and as such available surfaces for solar technologies. Also, the ratio of mix of commercial to residential buildings, for example, within a specific neighborhood type is important, especially when the goal is to achieve a net zero energy status. An optimal ratio of commercial land area to overall built land area can be between 23% and 32%. This is according to a theoretical study that we conducted, where according to this ratio, we were able to integrate enough photovoltaic panels to allow achieving net zero energy within a mixed neighborhood. Density is another important and critical factor in the design of solar community. Studies associate, in fact, increased build density with sustainable development, but this should consider cumulative effects of various additional factors of a compact development. For example, the land use, the transit accessibility, job availability within walkable distance, walkability, and others. There are other important elements in the design of a neighborhood that also impact their solar access and solar potential and their design as solar neighborhoods. This include green and spatial areas. Landscape can offer, in fact, solutions for the integration of photovoltaic panels as well as solar thermal collectors and allows really to generate more energy that can be utilized in these neighborhoods. Orientation of streets can affect the potential to capture and utilize passive solar energy as well as energy output of various solar technologies. And as such, they really should be considered from early design stage and the building around them, they should be designed to get the best performance with the best orientation. Now, talking a little bit more in details about the work that is currently ongoing in subtask A, we developed specific designs of archetypes to study solar strategies. Archetypes in this task are considered as representative neighborhoods that of existing or new patterns in different countries. This include repetitive patterns of commonly applied design, such as that includes streets, building types, shapes, density, etc. And here is an example of or commonly seen neighborhoods in North America, residential neighborhoods where we see a grid layout together with the attached and detached houses. Other examples of archetypes can be representing uncommon or innovative examples. We have a few of these that were also presented and proposed by the experts in subtask A, such as, for example, in Sinfonia in Bolzano, the campus in Norway, and so on. Other archetypes can be theoretical cases presented in literature or especially developed to study different strategies. And here are some also examples of theoretical neighborhood, and I will be talking a little bit about these and some examples of the results that we obtained in a couple of slides. A methodology is developed also to collect information about these archetypes, including building types, materials that are employed in buildings and building envelope, outdoor areas, and also materials employed in these outdoor areas, streets, etc. These information are collected in a matrix or what we call matrix. And this is a Excel form that can facilitate their input into various simulation tools, allowing us urban level simulations. Once the base neighborhood of each of the archetypes is established, various solar strategies can be then analyzed. Here now I'm presenting some of the theoretical examples that I just mentioned of a neighborhoods, what we call the neighborhood units, and these are small neighborhoods designed according to various sustainable measures and range from residential dominated neighborhoods to higher density neighborhoods with commercial centers that include different type of trades and different type of buildings. The study aimed here at analyzing various renewable energy and role of solar energy for thermal and electrical production. I want to highlight also that the PV were accommodated in roofs and some portion of the facades when available. That means when we have higher building, higher rise buildings, and STC or solar thermal collectors are accommodated in parts of the roofs when PV area allows for this, and in landscape areas. Results of this study shows that PV electricity plays an important role in fulfilling significant portion of the total electricity need of all the neighborhoods, especially up to 95%, in fact, for a small scale or less dense neighborhoods. Some neighborhoods with high density and high amount of commercial building needs additional land area to accommodate PV panels that fulfill all the electrical load. And this can be quite significant, about 80% to 85% as compared to the total land of the neighborhood. Some of the high density neighborhood as well require significant additional area also of landscape to accommodate the solar thermal collectors to fulfill the thermal requirement. In this example, some of the small neighborhood units that I showed before were combined together to, according to their electrical energy performance, to allow achieving net zero electrical energy. And in this case also, PV plays a significant role in achieving net zero electricity status. In all these neighborhood combination, the major portion of the PV electricity is supplied by roof-mounted PV systems. Also, the study shows that the on-site sources can supply between 19% and 45% of the thermal requirement for the neighborhood combinations, but we still need additional solar thermal collectors, especially in high-density neighborhoods and larger neighborhoods. And this landscape area that's required to install these solar thermal collectors is significantly lower than the examples that I showed before for the smaller neighborhoods. The landscape area can be about 15% of the total land of the neighborhood, which can be, again, as mentioned, much lower than examples before, but also more feasible from urban planning point of view. Now, coming to the design of solar strategies and their analysis, different solar strategies will be analyzed using the archetypes that kind of presented, or the archetype concepts that I just talked about. This include, but not limited to, integrated solar technologies in roofs and facades, landscape integrated solar systems that can range from very traditional standalone elements to more interesting and kind of a more designed. The workflow is developed to implement and analyze solar strategies, taking into account various factors such as spatial design of the neighborhood, the optimal surface areas, to integrate technologies, neighborhood operation, and interaction with the local energy system, both electrical and thermal systems. Coming to the deliverable of subtask A, there are a number of deliverables, but I want to highlight the most important. Two summer schools or fall schools are designed. One of them, a fall school, is already conducted in September, October of this year. and it was attended by about 14 PhD students from 6 countries that were trained in complex urban level simulations. Instructors from 9 different institutions were involved in the training. The next summer school will be conducted next year, hopefully in person in Calgary. The final deliverable of the subtask A, and which is still under development, the results and the analysis are conducted to get to this stage, will consist on a web-based database that present various solar strategies and their potential application in example of neighborhoods under different climates. These neighborhoods can be, or solar technology can be selected according to the type of the neighborhood, the available archetypes that were studied, and available results will be shown to give an example of how to apply these solar strategies and what's their impact. This can offer flexibility of design for planners, architects, developers, and other key stakeholders by presenting examples of potential solar solution for different settings. And with this, I would like to thank you for attending this webinar. And if you have any question, please direct these questions to the organization of the webinar, and I will be happy to answer them as soon as possible. Thank you.
Yeah, well, this was an interesting insight. I think we understood a lot about what case studies play, how important they are to understand the planning, the process, the tool usage when doing this complex neighborhood planning. So we will see how questions to Caroline can be also tackled by the other speakers. Otherwise, we will gather them as Caroline suggested. And also, I want to apologize for any inconvenience you had while regarding this video. It seems that some of our participants had either with audio or with video problems. So I hope that most of you were able to see it, and the recording will be for sure available at the ISIS website some days after the webinar, so you can listen to it in peace then one day. Okay, so we come to the next speaker. From Italy. It's Silvia Croce. She is postdoc researcher at the Institute of Renewable Energy called EUREC Research in Italy. Her research work aims at gaining insights into solutions for an integrated design of urban build and natural environment with a focus on outdoor climates, thermal comfort, energy savings, and renewable energy production. She's a building engineer, architect by training, and holds a PhD in engineering. So you see that this working group of Maria Wall is really a very interdisciplinary one. The participating experts have very different background because they look into the subject from all these different angles. Silvia will present the work being carried out within subtask B, which is titled Economic Strategies and Stakeholder Engagement. So Silvia, I'm looking forward to your presentation.
Thank you, Barbara. I will share my screen. Good. I hope you can now see my presentation.
Sure, we can.
Perfect. So, welcome everybody. What I will present today, as Barbara already mentioned, is related to the work we are conducting in subtask B in relation to the use of urban surfaces and the related benefits in solar neighborhood. So what we are looking at in subtask B, we are focusing actually on economic strategies and stakeholder engagement with the aim to foster the use of passive and active solar strategies, looking not only at the economic values, but also to added values and co-benefits that solar energy might arise. We have a broad range of activities, and in particular today we will look at some results and some work in progress in these 3 core activities, which are related to the use of urban surfaces in solar neighborhoods. Why are we looking at surface uses in solar neighborhood, and why are we actually trying to define the most suitable surfaces uses in such urban areas? What we would like to achieve is having a broader focus. So we would like to consider all the surfaces available in our urban areas, which, as Birbal mentioned before, are a very relevant but limited resource. And we would like to aim to the use not only for solar energy production or the use of solar passive strategies, but also for the integration of a wider variety of solutions. Why this? Because actually the surfaces of our solar neighborhoods and our urban areas have an unprecedented exploitation potential. We have seen from studies in literature that actually roof allocate approximately 20 to 25% of the total urban surfaces, and the surface of the facades is almost double. So by using all these available surfaces, we might enhance not only the energy efficiency and the production of renewable energy in our solar neighborhood, but also the positive environmental impacts. So what we are focusing on, as I mentioned before, is not only active and passive solar energy systems, but a broader variety of solutions which we collected and discussed among the task experts in the subtask B. When we refer to active solar energy system, actually we include not only the energy system from the building envelope, which are the wider known solutions, but also energy system from the ground surfaces, such as PV pavements and other solar electric collectors for ground surfaces, and also energy system for urban features, such as the acoustic PV road barriers you can see in our picture. And when we refer to passive solar energy system, we focus on passive solar heating and passive solar cooling. But we also broaden our focus to other solutions, as I previously mentioned. So for example, we have a green solution, which include not only vegetation on ground, but also green building elements, such as green roofs and green facades, and other innovative technological solutions, such as these microalgae panels for the production of energy. We also have a water solution which might be used in solar neighborhoods, from water bodies to evaporative techniques to reduce peaks of air temperature during summer, to water squares. We also included the potentialities to use urban agriculture, both ground-based, building integrated, or also other forms of urban agriculture, such as beekeeping in our solar neighborhoods. And last but not least, we also consider cool materials, so highly reflective and emissive materials, which allow to keep the surfaces of the building envelope cooler, and which are also strongly related to the solar radiation, and also other innovative solutions. We also consider, obviously, the presence in solar neighborhood of traditional uses and materials, which actually builds our urban areas, but also the potentialities for smart solutions. What then is what we then discussed in subtask B are the conflicts and synergies which may arise among surface uses. So the question we posed ourselves has been, can we integrate the solar active and passive systems with also other solutions in order to better exploit urban surfaces? What we did was to create a sort of matrix in which we analyzed conflicts and synergies among solar active energy systems and other solutions. One case is the one you can see in the picture on the right, a biosolar roof, which integrates PV systems with a green roof, which also acts as a cooling element for the panels, and so and helps in enhancing the energy efficiency. But there are also other solutions, such as multifunctional solar green facades and cool roof integrated PV. So just an example of what we would like to do in fostering the use of urban surfaces. This is the case study of an industrial neighborhood in Bolzano we are analyzing in the context of Task 63. And this is relevant because it covers a large portion of the city of Bolzano. And what we would like to propose through our activities in the task is a methodology for moving from the current configuration of the district, which actually integrate the common surface materials and some solar active systems, to a surface use pattern. So a configuration of the district which integrates also more innovative solution in which the use of solar active system is enhanced, and there are also other solutions such as the green solution. How this might be done? Through several methods, so integrating on-site monitoring, the use of environmental tools, and also multi-criteria approaches. And what is then done, of course, the results are analyzed. Here you see some example of analysis with relation to some environmental parameters, so air temperature and human thermal comfort, but also the analysis of the solar potential and so on and so forth will be carried out. So what's coming next in relation to these activities in subtask B and in task 63? First of all, by the end of February, we will release our first deliverable. They'll deliver a report on surface uses in neighborhoods, focus on how to define the most suitable uses, but also avoid conflicts and create synergies. So if you're interested in the topic, keep an eye open and on our website, and you will soon find our first deliverable. But we will also focus, as in the example I shown you, on the individuation of methods for the definition of the suitable urban surface uses in solar neighborhoods, based obviously on site-specific objectives. And we will also focus on the benefits, not only the financial ones, but also the environmental and the social ones, which then integrated use of urban surfaces might provide in solar neighborhood. And in relation to this, we are actually working also on the identification of the potential co-benefits related to the use of urban surfaces in solar neighborhood. What we highlighted in our discussion and work in the task in these 2 years is that actually urban surfaces are a key resource to tackle several issues related to urbanization and climate change. So they offer benefits not only related to the production of renewable energy, but also to other sustainability benefits, for example, the availability of rainwater and the food provision, but also they offer benefits in fostering climate resilience. So for example, they allow to improve the management of urban climate, to preserve habitats and biodiversity. They contribute to the management of stormwater and also to the amelioration of air quality. What has been the first step in understanding the relevance of these potential benefits in solar neighborhood? It has been a survey which aimed to identify priorities in the design and implementation of solar neighborhood. We actually asked to our participants to evaluate 55 urban challenges from 0, which means not at all relevant, to 10, which means extremely relevant. We've done and we are doing this in 2 phases. In 2020, we opened this survey just to the Task 63 experts and we got 25 responses. While this year in 2021, we are diffusing this survey also among external experts and practitioners. And this activities is still ongoing, so you are really welcome to contribute to this. While we decided to open the survey from to external stakeholder, it has been because from the analysis of the responses we've got from the Task 63 expert, we noticed that actually our point of view is quite limited. Many of us are engineer or architects, still have a very focused experience on design, urban planning, and also solar active and passive systems. And so some of the responses we've got on the relevance of these urban challenges might be influenced by our background. As I will just bring you some of the examples of the results from the survey carried out in 2020 among Task 63 experts. One of the area we focused on is climate change. Actually, experts perceived as very relevant issues related to climate mitigation and climate adaptation, but consider less relevant issues related to water management and also flood management and increased urban ventilation, which of course in other cities and in other area of the world might be more relevant. Another field investigated by the survey are environmental aspects. Also in this case, we got some results which might sound surprising from you audience external to the task. For example, solar access and optimal use of daylight were among the challenges and benefits perceived by the expert as more relevant, but actually they some other challenges and benefits such as visual comfort and biodiversity preservation received a score, an insufficient score. So obviously, this is related to our focus. We are working on solar active and passive strategies, but this might obviously not reflect what is the external perception of what the solar neighborhood might provide. And that's why we are distributing the survey among external stakeholders and why we are also asking your inputs. Another aspect we analyze this, and we are analyzing is also resource management. In this case, the management of renewable energy and the provision of clean and local energy consumption were identified as the most relevant, while waste reduction and food security were less considered. If we move to social aspects, also in this case, we got some surprises. The presence of public spaces and an increased quality of life for health and well-being were highly considered by the experts. But, for example, acoustic or also gender equality received a very low score. We also analyzed economic aspects. Here, peer-to-peer trading of energy and prosumer-based business models are perceived as very relevant by the task experts, while real estate value increase and the increment of energy prices less. So, as I mentioned before, the survey is open to everyone and it will take approximately 10 minutes to complete it. The answer will be anonymous and then the results will reported in an aggregate way. So feel free to contribute to it. There is the QR code here available in the slide, and when the slide will be circulated, there also the link. And with this, I thank you for your attention, and I hope you will keep focusing and following our work also in the future, and be interested in our future results. Thank you.
Thank you, Silvia. Very nice. Interesting results from this survey, I think, on understanding how the different factors play together, because there are, you know, like competing effects in urban planning. So we come now to our last speakers, which will be a tandem. You know, they also chair the subtask C together, which is on solar planning tools. We have Martin de Boll from France. He is a researcher at the Loci laboratory. He's mechanical engineer by training, and his research focuses on applying thermal and fluid science on the deployment of solar energy in urban environment. And he is joined today by Jori Kande, assistant professor at the Division of Energy and Building Design at Lund University in Sweden. He is an architect by training, and Jori's main research interests are on the integration of solar energy in cities and circular building designs. So they will join together to present this work, which is done in solar planning tools in subtask C. Yes, the floor is yours. Martin, you start.
Can you hear me?
Yes, we can hear you and see your screen.
Perfect. Okay. So thank you a lot. So maybe as you just saw, solar neighborhoods have a very huge potential, and the use of solar energy is very important in a district and in neighborhood, but it's also very complex. It's complex because it has a wide, you can have a wide variety of use of solar energy and also of surfaces. And as you could have understood, it is crucial to use solar energy smartly for many different aspects for the energy transition, to ensure thermal comfort, and also in the context of climate change. To ensure this good use of solar energy, we need tools, and this is all about the subtask C. What are the tools, and how can we use tools and workflows to apply it to solar planning a neighborhood? The idea is here to bring some knowledge to support decision in this complex environment, and we focus here on active and solar potential, and active and passive solar potential. Just an illustration of the complexity could be seen here from an illustration of Emily nodes. Here you can see that in the planning of solar energy neighborhood, you have many different factors that appears, and one of them is the scale. Because if you take the urban scale or the building scale, you have many different things to address. The data is not the same, the quality of the data is not the same, and you have different layer of tools that you can use, and you also have different type of actors and users at each steps. So in what follows, we will show you some achievements we have been doing in the subtask C. One about gathering smart and relevant performance indicators. One about trying to gather workflow stories to identify current tools and best practice, and some comparisons of current tools.
Yes, thank you, Martin. Yeah, so one of the first things that we did within the task was to gather something that we called national common indicators. So they are basically key performance indicators that are very specific to the participating countries, and we gathered those common indicators that were both related to the active solar energy potential, meaning, for instance, the solar thermal potential or PV potential, but also on the passive solar energy potential. And here you see one of the tables that we found from looking at legislation in the participating countries. For instance, when it comes to direct solar access. So in some countries, the legislation state that, for instance, a bedroom should have at least 2 hours of direct solar access at a certain date. While other countries might say that, well, at another date, it's maybe 1 hour or 3 hours. And there are pretty big discrepancies between the countries, and even though they are at the same kind of latitude. When it comes to the active solar energy legislation, there are not many countries that actually prescribe when you are constructing new buildings that you have to install an active solar energy system, being it like PV panels or solar thermal panels. So it's kind of interesting to see the difference between the different countries. Can you do next, Martin? Yeah, so then we looked at what are the implications of those different common indicators. That's why we took 3 national common indicators to kind of showcase the implications of those common indicators. So we took a rather random courtyard building, and then we simulated this courtyard building at different latitudes. So meaning we looked at the different solar conditions at the different latitudes, and then we applied the different national common indicators to this. And then you can see on the right hand side, for instance, this graph here, that those is the share of the courtyard facing facades that are not meeting the thresholds of the national common indicators. So of course, the higher on the latitude, the harder it is to reach those thresholds, and this you can see pretty well, I would say, in this graph. So and again, it kind of demonstrates the fact that even countries at the same latitude might have a very different approach to what solar access is and what level is considered to be a good solar access. Next, please, Marta. Then, parallel, I would say, to gathering the national common indicators, we also were interested in how do key actors in the design process of solar neighborhoods use tools, and that's why we have something that we call the workflow stories, where we actually gathered this. Yes, thanks, Marta. So this is one example of a neighborhood which was evaluated by, in this case, a commercial consultancy company, where they looked at different performance indicators. For instance, how much of the facade reaches a certain threshold of direct solar access. So I don't know, could be 2 hours on somewhere in January, or what is the irradiation on all the surfaces. Those kind of things that they have worked on. But then what we were interested also was not only the indicators, the key performance indicators, but also which tools they have used to assess those key performance indicators. So for every of these workflow stories, we asked the people that wrote these workflow stories to provide input for the tools, but also output, and also describing the workflow. So different. Sometimes you need, since the urban planning is a rather difficult process, it might be that you have, as Martin already said, different data available with different quality. So it might be that you have to use different tools in order to kind of give answer to the performance of a neighborhood. Can you go next slide, please? Another example is this by white architects in Sweden, where they are demonstrating like an in-house tool. So, for instance, architects within the company are using different 3D modeling environments, but they all want to kind of assess the performance of a neighborhood or a building. So what they did was here that they kind of developed a workflow that could be fed by different 3D modeling environments, but the outcome would still be the same performance indicator. Next, please. Or here's another example of a advanced solar map where one of the task experts kind of developed this solar map where you can get more information about the conditions for your real estate property if you're interested in installing, for instance, a PV system or a solar thermal system. Yes, next, please, Madame. And here also, like, this is not very it's not very simple to do all these kinds of simulations, and you have to kind of find a way. Sometimes you even have to develop your own modules in order to get the result. So, and here's just an overview of some of the other workflow stories that we gathered from different companies or from academics, where people have used different tools to kind of to analyze the potential of solar neighborhood. Yes, Martin.
Okay, so I will finish with one last thing that we want to study with we carried within the task. So as Yuri just mentioned, there is a lot of different tools, and one thing we thought was to try to use a maximum of these tools doing the same task, what we call here a benchmark study. So for this study, we set up some rules. The rules are quite simple. We use two different districts, one which is like a grid district, and the other one which is more random. It's happening in Geneva, and we provide it to experts. We provide them with the geometry, the location, as well as the weather data. So basically, we are supposed to have for everyone to have the same simulation initial condition. Regarding the tools that we used, here you have a list on the left-hand side of the tools that we have been benchmarking. One thing that may be interesting here is that these tools were not, at the origin, they were not designed for the same purpose. Some of them were more designed to perform day lighting study, whereas other one were more about energy in cities, or even there is a solar map of Geneva that we just talked about. And there is also one beam and one model which is used for weather prediction in physics. Here you have an illustration of some results that we got. So I took the case of this district, and we focus on the central building here, the building 5. And what you can see are the distribution of the irradiance, of the hourly irradiance on each of the facade. So on the roof here, and here on the west, north, south, and east facade. One of the first things which is very interesting is that even though we try to give the exact same initial condition to each of the tools, then we have as many different results as there are tools. So you can see that there are no two identical results in these plots. So this is one of the first very interesting point, because actually all these tools are quite, they are reliable, they have been validated, but you can see that even if they have all been validated, we still have some differences which are sometimes far too being neglectable. We can see that there is usually less variation when there is direct sunlight, for example, on the roof or on the south. We have variations that can reach up to 150 water per square meters. And also we don't have one tool which is constantly over or underestimating the predictions, the solar irradiation. Another way to analyze the data is to draw this kind of facade mapping. So here I went back on this homogeneous district, and this is the east facade at 10 and 11 a.m. So what you can see here is actually the distribution of the irradiance. When it's red, it means that there is a lot of a high value of irradiance, so usually it's direct sunlight, and when it's yellow, it means that it's a shaded part of the building. And you can see once again here that we have very different behavior, and we don't have two identical results within all our results. We have different behavior. Some predict a sharp distribution, such as in VMET and Quetzal, or some predict a smooth or some, let's say, fuzzy distribution, for example, in Deluxe or the Illuminae. And this is due to many different ways to model that I won't talk in detail here. So it could be due to the physical modeling, also to the way to handle the data and handle and how the workflow is built. So to finish, here we are the midterm of the task. And what we plan to do is a roadmap for the improvement of the workflows and the solar planning tools. So here we showed you some of the results we got, and all these results, all these first results and studies are here to set a state of the art, a status. Where are we now? What are the tools? What are the KPIs? What are the how do different tools perform compared to each other? Then in the second part of the task, we want to, from here, to have a vision of what we should do and to set different milestones in order to improve this workflow in the context of a solar neighborhood. Thank you for your attention.
All right, welcome everybody to the live Q&A session on IEA SHC Solar Academy Task 63, the webinar on solar neighborhood planning. We are now good to go, and I welcome all of our speakers to the panel, and of course everybody that's joining us today. Thank you for having watched the pre-recording, and we're going to now start the Q&A session. Unfortunately, our moderator Babel app can't be with us today, so I'm going to take over for her. And yeah, if I could please ask the panelists to turn on their cameras and turn on their microphones so it's a bit more lively around here. Thank you. And then for the audience, if you have any questions, please put them in the chat box, and then I'm going to get them to the panelists. Right. Thank you, everybody, for coming online. The first question I want to start off with is to Maria, and it came in from somebody, and they are asking, could you please again give us your definition of a solar neighborhood?
Yes, well, you saw that I mentioned that neighborhoods is a group of buildings within a specific geographic area, and this neighborhood, if it's a solar neighborhood, I would say that it's a neighborhood that uses solar strategies to achieve sustainability goals like low carbon or low emission, 0 or plus energy, or whatever is set for the neighborhood and the city. So that's how we think about solar neighborhoods.
All right, thank you, Maria, for that first one. And then there's a question following that one right away. Does your task then also include user perspectives and policy measures when you're engaged, or when and how you're engaged citizens?
Yes, it does, and maybe Sylvia can explain something about this because it's part of her subtask.
Yeah, actually, it's a very important factor for mainstreaming, or at least distributing more solar neighborhoods. This is something we are working on in subtask B. which focus also on stakeholder engagement, is still a work in progress, but we are taking some of the projects we are involved in as examples to understand how citizens, but also other important stakeholders in urban areas may be involved in the design and definition of solar neighborhoods.
Thank you, Sylvia. Could you maybe give us a few of your, I don't know, maybe best practice examples you've seen, or policies or measures of engagement that you have come across that you've found exceptional or leading in that regard?
Well, it's we have seen it's highly depending on the context you're working on. So it's highly depending on the city, the involvement on the citizen, also the involvement of the municipality. What we saw it's really a key factor is involving the citizens, and in particular the citizens who are living or will live in the neighborhood from the beginning of each intervention, being it both a new construction or a renovation intervention. And it's really important to explain them what is being done and the reasons why this is being done. Otherwise, it's very difficult to allow people understand the reasons why a certain design or certain solutions are adopted. So, for example, workshop or informative session are really important.
And Yuri, Martin, and Maria, what's your experience here? Do you encounter this in your own work as well? Or is maybe the task even developing, I don't know, a guide or something along those lines for how to meet citizens that, as Sylvia pointed out, should actually then live in that solar neighborhood?
I could go with some of the experiences we have, which is so we develop a tool to predict solar energy for a big area, which is Geneva and around, and we have one of the goal of the tool is to provide the project is to provide a tool for every actors to be able to take its own decision. And we often come across municipalities of small municipalities of some hundreds or maybe thousands of inhabitants that are very interested in having solar neighborhood, deploying solar energy, but they don't have the skills and the knowledge. So what we try to do is to try to provide enough data, enough good enough tool, and also understandable tool, so that they can make their own decision without having to have experts, or at least like not big experts. So yeah, this is something we encounter, is many municipalities that wanted to do something and that they didn't have the tools and the data to do it. And so this is also what we would like to address in this task, is to have this workflow which are understandable by experts but non-experts, so that everyone can master or understand what is done, and then we can unleash the full potential of solar energy.
I can maybe comment that at the end of the task, we will present a number of case studies, like examples of solar neighborhoods, real cases that apply different strategies for things that we have done and what they have done regarding solar energy, but also on different corporations and tools and things. So you will see later in the task in 2023 that will be published, all the cases with different strategies, depending on country and the situation. It will differ, the different cases. Thank you.
That's right, of course. Yuri, did you want to comment on it as well?
No, I think Matan already addressed some of the things that are interesting to this topic.
Good. Yes, thank you. Yuri, I'm going to follow up with a question for you right away. Or maybe it's more a question to Yuri and Martin. Do you also address the usefulness of renewable energy in real time, or is it a net zero on a yearly basis? How do you go about it?
I know, Marta, yeah, I can also start. Doesn't matter really. I mean, what with a lot of tools that exist today, they are advanced enough to give you. It depends what you call real time, but on an hourly basis, it's. I would say most of the tools can actually address this time resolution. But on the other hand, a lot of the not legislation, but more of the concepts are on annual basis, so they are aggregating like the hourly values. So in that sense, we look at a much longer time resolution. So the tools are actually, I would say, able to do this on hourly basis at least, or even smaller time resolutions. But a lot of the concepts like the net zero energy building, they are often considered to be at an annual time resolution. I don't know, Martin, if you can add something or.
Yeah, so I maybe yeah, to keep going with what you was saying. So as he said, like some tools are not limited and they can do resolutions that could reach second, for example. It's not a matter of what the tool can do, it's more a matter of computational time, so that if you want to do a simulation with a time step of 1 second, then it's very difficult to simulate 1 year. And you cannot simulate one city for 1 year at a time resolution of 1 second, or you have to do like drastic hypothesis on many things to have your simulation ready. So it's really depending on what you want to do. Actually, as Yuri was saying, the concept and the legislation and indicators are calculated on. It's either on an annual basis or on one specific moment. It could be 1 day, for example, for the daylight, it's 1 day during the longest or the shortest day of the year. So it really depends on what you want to do. But this is something that should be addressed, especially if you are looking at the matching between the loads and the energy production, especially with solar, because solar energy can varies by 100% in 1 second, and it's more or less the same with consumption. And yes, so it's something that needs to be addressed, and which is yeah, I think this is one of the scientific challenge to be able to well address this time resolution at large scale in the future. And one also point which is very important is also when you talk about real time, there is also the aspect of the climate change, which will change also the weather. And this is something that must be considered as well in the weather file or the weather data that you use.
Mm-hmm. And we've got a question exactly about weather and weather forecasting. One of our listeners was wondering, what is the weather file that has been used in your simulations? And could it potentially been from Energy Plus database?
Yes, so it was so we made a benchmark, as you saw, with different tools. And the thing is that, as we were saying, some of these tools can simulate very short period, but are very time consuming. And so you cannot simulate more than 1 or 2 days. And other tools are designed to simulate 1 year, several years. So what we did is that we just asked to simulate for 2 typical days. And these days were built on based on the Energy Plus weather file for the Geneva location. It was not exactly the same, because we took the data for 1 month, the month of February, and we built a typical day from the month of February. So this is something that is done, which is one way to reduce the time, the simulation time. Instead of simulating 365 days, you only simulate 1 day per month, and this day is a typical day of the month. So you reduce by, I don't know, 30 times your time, your simulation time. Yeah, so the answer is yes, and yes, we used Energy Plus, but we slightly modified it for the matter of our study.
Thank you. Yuri, you are nodding. Do you want to comment, or is that just a yes, I agree?
No, it's exactly what Martin said.
Okay, awesome. You're on the same page. That's great.
Yeah.
I got a question to everybody. We've got one listener, and they write, I'm in the process of helping a municipality plan a district heating system. What are the main deliverables from Eurotask that could help me and be relevant to my work? So it's more on the heating side, but still it's a neighborhood issue. And if we assume it's solar heating or solar-based heating.
I can maybe just start to say that, yeah, you have to consider economy and what is possible and okay to use if it's solar thermal systems, if you already are connected to a district heating system, or maybe the district heating system includes large solar fields with, so areas with solar production elsewhere. So it's really depending on the situation in the area, or if you would go focus maybe on solar PV systems for electricity production, then if you have, so because you need electricity as well. So that could be one thing that you need to think about. And then you have, of course, all the other things like daylighting and comfort, thermal comfort to look at indoors and outdoors. But that's separate from the energy system. Maybe someone else has comments.
So maybe in addition to what Maria said, so at the end, I mean, we are also within the task working on case studies, and case studies are project for solar neighborhood. And within these case studies, we try to talk about a lot of points. What are the actors? What are the key performance indicators? What are the lessons learned? Who was involved in the project? And I think this could give some hints, even if it's not here we talk about, in our case, we talk about solar neighborhood, but for district heating, then you will find some similarities in the actors you meet, in the performance indicators that you want to look at, and also in the lesson learned. How do you involve citizens? How do you involve the actors? What was the error not, I mean, lesson learned, what has been done but can be better done on, and what has been well done also. So this is all the things that could be, I think, useful.
A comment again, then, that these, of course, if you are doing it right now, we don't have the case studies ready to look at, but in the future, within 2 years, we will have the results of these that are ongoing, and then we also will have some results regarding different typologies of neighborhoods and what could be suitable strategies, solar strategies for these with the analysis, and that's dealt with in subtask A as well.
Thank you. I got a question from Maria. How are you dealing with the changing needs in regards to electricity and the future electrification of your neighborhood? So your neighborhoods now might look very different from what your neighborhoods might look in 5 to 10 years even. So how can the task deal with that?
Yes, we there will be different ways to handle this, because one strategy we have is that we are looking at existing typical neighborhoods, and then what we will do is to work on how can we improve these to be with high goals regarding sustainability, and including a lot of solar strategies. And so we will have kind of reference cases, today's cases, and we will have future cases, what is possible. And in this way, we need to have different load profiles, of course, for the situation today, but also to look at what we will have in the future.
A bit of a tricky question came in. So do you have municipal governments, laws and regulations that support your work and your projects? Or, and this is the tricky part, are your projects a bit of scattered experiments throughout, let's say, Europe, for example? So obviously not my words, but so how is that? How do you find the support and the policies that are backing up your projects? And I think that's a question that could go to all of you.
I can start with just a small comment. I mean, I don't. Let's say that I mean, it's just some small experience, but municipality they can. In our case, we have some of the expert participants that are dealing with projects which are supported by municipalities. So I'm not sure. I mean, Maya will tell that we have municipalities which are directly within the task, but within the experts, we all work with municipalities that supports our project, and in that matter support also the case. So that's it. So we have inputs from municipalities, and then we also work with them to provide them tools that can be useful for them. So maybe this is just a bit of answer, but if you have more to add.
I can just comment that, I mean, there are kind of voluntary goals and strategies in the municipalities and in different regions to reach sustainability goals. And this is, of course, helpful for us since I think the interest is rather large in cities today to have a good planning and so on. But it's very tricky to handle all the aspects and work on that. So we will try to support them within our research areas. But of course, they have a lot of other things to work on as well and decide about.
Okay, and then I'm gonna. Oh, Yuri, did you want to comment?
No, I just want to say, like, a lot of the municipalities, it also depends very much on the country, how the country is like governed. Because, for instance, I know some countries, they have very strong regional legislation, while some countries do not have this. For instance, in Sweden, like all the municipalities, they have to somehow relate to the national legislation rather than there is no regional legislation. So it's also different from country to country. But I would say that they have to find a way how to apply the national legislation. And I was giving the example before also, like within the European Union, then there is a lot of they kind of try to streamline daylight recommendations for all the member states. So the local municipalities, they somehow have to relate to this. So this is going to change. So in that case, there's like a kind of a top down and there is a bottom up at the same time, I would say.
All right, thank you for that. And then just a second tricky question. we got from somebody. What do you perceive as the biggest challenges in your work right now as you work on solar neighborhoods? Or maybe also advantages. We don't want to just have the tricky ones, but maybe try cover both. And yes, I have to tease a bit.
I think, I mean, what I personally have seen is it's a very complicated and long process. The planning process, for instance, is a very long process. Normally, it takes 10 years to go from the first sketch by the urban planners to the building actually built, or even longer sometimes. I would say normally not shorter. And there are so many different actors that all want different things, and they kind of are optimizing the process in a way that they benefit most from it, which is fully understandable, but it makes it sometimes very complicated because of once they all turn in the same direction with the same goal, then you kind of reach what you want to reach. But otherwise, if you don't do this, then it might be that people have good intentions, but in the end there is no solar energy system installed because of different things that could be legislation, could be investment costs, or they kind of find it hard to see the financial benefits, or for instance, real estate developers that think that if they are going to sell the building after a while, then they cannot see the return on investment, etc. There are many different things that I can think of here that could make it more difficult. But on the other hand, as I said before, if everybody has the same goal, then I think it could be rather well done. So.
Yeah, I fully agree with what Yuri said, and on top of that, you have all these actors with different goals and sometimes competing interests, and you have this long time frame. And you also have something which is very interesting in terms of research, which is that sometimes you have some criteria, let's say solar energy consumption, which can be quantified. So you can like count like how many kilowatt-hour you use, how many kilowatt-hour you produced. But there is also many criteria which are subjective or qualitative, such as maybe comfort, that can be sometimes quantified, but it's not a real an exact science. There is also aesthetic in terms of if you like seeing a PV panel or if you don't like it. There is all this time of willingness, like if you are pro environment or if you are not contra environment, but depending on your what you are. And all of this makes it very difficult, because what is only qualitative then is very difficult to model in tools and in workflows. And so you have to find way to try to model it through some I mean, I won't enter into the details, but some what's called fuzzy logic or some statistics. But it's also something that is very interesting to have these subjective and objective criteria within this type of model, and that makes it complex, but also very interesting in terms of scientific challenges.
And added to what Martin said, I think another point which makes it very challenging but also very interesting is the need of approaching this kind of design with an interdisciplinary approach, because relating exactly to what Martin said, there are so many different factors and also sometimes competing, which really need an approach coming from different disciplines. So it's not just anymore having urban planning planners or architects involved, but there is the need also, for example, for having us researchers in some cases, but also having people coming from other fields, not only just engineering, but also social sciences or biological sciences, depending on the neighborhood, the objectives on the neighborhood, and what is being constructed and designed.
And a small comment that it's challenging, yes, but I also see that we have a lot of benefits available of planning early in neighborhoods when we plan neighborhoods and take it into account. It's not about only about energy. It's about people's health and comfort and everything. So so this is really, and how people will like to live in a neighborhood or work there and so on. So it has a lot of, it's really interdisciplinary, and it's a lot of things that we could benefit from if we plan well.
Awesome. Yeah, that sounds really interesting. I see the pull and shove between the researchers and then the real life experience in a neighborhood. That sounds awesome. I'd like to close out with one last round of, let's say, a question or maybe more of an outlook, and that is looking ahead to the future of the task. So you've got 2 more years, if I understand correctly. What are your projects and what are your next steps for the task? What's in the plans?
We have, I can start just as an overview, say that we have different reports with results in different subtasks that are in planning. And for the, as I mentioned, subtask A on solar strategies and concepts, the plan is to really to analyze different types of neighborhoods to find out suitable strategies for different boundary conditions and different situations and countries and climates. So that will be part of the next work for that. And also a course for PhD students and advanced master students recently were done, and there will be another one next year. So that is in planning. And then I let the other participants here talk about their subtasks.
With regard to subtask B, as I also mentioned in the presentation, we will continue the work on urban surfaces and in particular on benefits, also exploring the economical success factor. But as we were discussing before about the great and important role that citizens and stakeholders have, the future work will also address on one side the stakeholder engagement in the design and definition of solar neighborhoods, which will become also part of some guidelines which will be published in a deliverable. And we will also focus a bit more on the financial mechanisms which might be able to sustain the development and will be very relevant in the future of solar neighborhood.
Yeah, I think in our subtask about tools is we are still gathering some workflow stories, and but we also are starting to develop a roadmap for improved workflows and workflow, like kind of tool workflows, and try to understand how they could be improved.
And I can comment
Maria
on sorry?
You go, Maria, don't worry.
Okay, I can just comment on the case studies. That is also part, as we already mentioned several times today, that we work with all the subjects we are studying and the challenges we have. We will deal with them also together with municipalities and other key actors in different case studies in different regions and countries. So this is a joint part also where we really collaborate among the topics we have and our research and to implement and test in the real life. And Silvia, maybe you want.
I was also saying exactly the same about case study. So.
Okay, awesome. Well, thank you for that outlook into the next 2 years of the task. And I think with that, we can come to an end of today's Q&A session. So thank you again to Maria and everybody on the task for joining us and for sticking with us and answering all of our questions. And for our audience, just a heads up, the recording of the webinar, which will then include this live Q&A session, is going to be available to you online in a few days, and we're going to have it available both on the ISIS homepage as well as on the IEA SHC Solar Academy homepage. And of course, if you want to learn more about the task has their own homepage, as you've seen a few times now, so check them out there. A reminder to our ISIS members, you already have unlimited access to all past webinars on the ISIS membership homepage, so always worth looking there. And then there's one final announcement I want to make today, which is something we are planning for 2022, and it's going to be together with the IEA SHC, and that is Eurozone 2022, our next big conference that's coming up. It's going to take place in Kassel here in Germany at the end of September next year. And the call for papers and the call for participation is going to come in early 2022. So keep an eye out for that. And with that, I want to thank everybody for joining us today. We always welcome your feedback. So if you want to write to us at public.relations@isis.org, any comments or questions you have about webinars or other ISIS events, there's going to be a tiny survey that's going to come your way after the webinar. And of course, you can always find us online on the different social media channels. Yeah, and I think with that, thank you again to the speakers, and I release everybody into a good day or a good night, depending on where you are. And thank you for joining us. Bye.
Thank you.